So I'll give an oral or a simple introduction to what DVGW and KIT is. KIT is the Karlsruhe Institute of Technology. It is the largest research university in Germany in terms of funding, and and we are involved in several hydrogen projects, from hydrogen production to hydrogen distribution, consumption, everything. DVGW is the German Association for Gas and Water. It is the legally mandated body for standardization of gases and water in Germany. It is a big organization. We have 14,000 members. All the energy producers, distributors, companies, anything that has to do with gas through a pipe or a device using gas is a member of DVGW. And we use the DVGW standards for everything related to gas in Germany, and hydrogen is also gas. So, and the DVGW Research Centre for KIT is a very unique institution. It is a combination, it is a collaboration between KIT and DVGW, where the academia is connected to industry, both ways. That's it. So now I'll go directly to the topic. My presentation has a very specific structure today. So we have a lot of definitions floating around. So I'd like to clarify what we define as hydrogen valleys, etc. in the first part of the presentation. Then we do the methodology. I mean, a question was asked in the beginning from the ministry. How do we set up an energy hub? Do we keep it in the ports? Do we keep it inland? Where do we do it? So we have been working on this question for the last 10 years, and now we have a very clear answer to how we go about doing it. That will be the second part. And the third part will be 3 very specific insights from our projects. We are not going into the details of every single project. We are into around 25 projects. It will be too much. But from all the projects, we have taken, or I have taken 3 specific insights which will be shared. And lastly, I'll give us a very important question: what to do in India, or can we do it in India? So the first slide. What is an energy hub or an energy system or an energy valley? How do we define it? In our case, an energy system is a real-time system where the energy production components, the storage components, distribution components, the power to X systems all interact. So for example, it'll look something like this. We have an area of energy production. We have all the networks. We have the hydrogen network in the future, the gas network, the electric network. We have the district heating network. And we can, for example, I can't see myself. Okay. We can set in this system so many parameters. For example, we can set the grid. We can dimension the grids. We can see how the gas grids, the hydrogen grids, we can dimension all of them. We can see which sectors are relevant. For example, we can specify how the buildings are, what kind of heating devices are used in the buildings. We can specify how the mobility systems are, what kind of fuels are used in the mobility system, and we can also specify what is the industry doing, what kind of industrial heating systems are needed in the system. We have profiles for everything. For example, profiles are time dynamic. And we can set the storage system. We can put any number of batteries, hydrogen storages, gas storages into the system, and we can make all of them interact with each other. For example, we can do sector coupling. We can convert power to gas, gas to power, gas to heat, power to heat. So many different pathways are possible. So this is a generic definition of an energy system, and this is what we are using in every single one of our projects. Now, the second very important, is my slide not going? Yeah. Second very important definition is of a system simulation. So this is, for example, it's very, very difficult to test these systems in the grid on a real physical location. One, you can't take an existing location because it'll spoil the grid, it'll cause trips in the grid. And in many cases, most of the hydrogen hubs are only in the planning phases. It's not yet there. So what we do is we have models. We have real-time models where all the components of the energy system are available, right from electrolyzers to all the heating devices, all the mobility devices, and then we simulate them. And once we simulate them, we get 2 kinds of results. One is the short-term result, What happens if there is a sudden cloud coming into the solar plant? Will the solar plant give the output? What if the wind does not blow? Is the storage system empty, etc.? It's very short term. And then we have seasonal results, and this is actually more important than short term. What happens between summer and winter? Can we produce more hydrogen in summer and then supply them in winter, or things like that? So all these results are very specific to the energy valley under consideration. It's very important. And uh, we get so many seasonal results. What happens to the demand and supply? How does the cost evolve? Because if you're taking up intermittent energy supply, then costs are also intermittent. How do these things evolve? And what is the greenhouse gas emission from the whole system? So these are the kind of results that we get from the system simulation. And the third, and the most important decision-making tool that we use in our models is called the energy trilemma. Many of you might be aware of this term. Energy trilemma it's a yardstick that we use to rate energy systems. This answers the question whether we need the system in an inland area, whether we need it in a port, what should we do with it? And energy trilemma essentially means there are three types of parameters we look at. One is the cost. The other one is the security of supply. Do we produce enough for the region, or can we produce more than what is required for the region? And the last one is greenhouse gas emissions. And in any region, to have a functioning hydrogen valley, these three parameters are important. If it is costly, nobody is going to make it. If there is no security of supply, it will be a very difficult system to manage. And if does not have GHG reduction, it will be trouble for the decarbonization strategies. And now the question is, how does this evolve? For example, we have several studies saying that some people say hydrogen might be, the next best thing. Some people say, no, EVs will come into the society. Some people say, no, hydrogen and EVs won't come with fuels. Now the question is, which one do we use in an energy valley? Energy valley is a mixture of industries, buildings, and mobility. So you can't say that, there is one thing fits all kind of solution. And what we generally do is we use scenarios. Scenarios predict the future. We have a strong working relationship with Fraunhofer, and they predict how the future societies will be. What share of industries will use hydrogen? What share of mobility will use EVs or e-fuels? And what we do is we take this data and then we plug it into our hydrogen valleys and then see how the valley responds dynamically. So this is the three definitions that I'd like to start before going into the methodology. Now coming to the working methodology, what do we do this information? How do we go on in our hydrogen valley projects? In all the projects, the method is the same. First, we do the system modeling. We go into the area. We take everything from the area and we model in the as-is condition, as it is today. Then we modify the system based on the scenarios. What will come in the future? Will it be all hydrogen? How will the industry transform? How will the mobility transform? How will the buildings transform? After that, we simulate the models and analyze energy trilemma. We analyze what will be the overall costs of implementation. We analyze whether the supply produced in the region is enough to meet the demand, and we analyze whether the whole thing will be carbon neutral or carbon negative or like that. Armed with this information, we go into the city. We give them this information, and then they can take the decision whether it is feasible to build a hydrogen valley in a specific location. That answers the question whether we need a valley in an inland area, whether we need a valley in a port. What happens if we keep a valley near the production center? What happens if we keep a valley near the consumption center? I'll not go into the specific, and a very, very important part of it is how do we test this? Most of these are models, these are simulation models. So for that, KIT has the only such facility in the whole world. This is called the Energy Lab 2. It's a cluster testing system where we have all the components of a potential hydrogen valley. We have all types of electrolyzers, SOECs, PEMs, and alkalines. We have all types of e-fuel systems. We have jet fuel synthesis. We have power to gas, power to fuel. We have biomass gasification. And we have a control system at the center that can adaptively switch on and switch off these things so that it imitates a future hydrogen valley. So once we have the trilemma on board, we have the simulations on board. Here's where we test it. And then with this information, we can be very sure that the adaptations that we provide will work in a real hydrogen valley or a real valley. Now, I'll not go into the projects and project specific details, just 3 insights from all the project. First insight, all the valleys are heterogeneous. Every single valley has its own fingerprint. We need to go and model each and every one of them. How the industry in a particular region transforms, how the mobility in a particular region transforms, and how the buildings transform. The second insight is that for any hydrogen valley to work, the production and the consumption has to be linked by the networks in between. There are 3 networks, the gas network, the hydrogen network, and the electric network. And we need standards and testing for that. This is where DVGW comes in. We make the standards and we have a huge testing department. So after we have this information, we go into the standards and testing. And the third insight is that we can never minimize all of them together. It's Pareto optimal. That means we'll reach a point in a hydrogen valley where we cannot reduce costs without negatively affecting emissions, or negatively affecting security of supply. What we do is we quantify it and give it to the decision maker. This is what's the cost, this is what is the GHG, and this is how the supply security will look like, and they can take the decision. And however, it has to be done specifically, separately for each system. And now the $1,000,000 question, what to do? Can we do this? Can we adopt this methodology in India? Short answer, yes, we can do it. We can use the same methodology for any location. We're using the same methodology in all our projects, but it has to be done by a multi-agency ecosystem. We need to have all stakeholders on board, and we need to have some kind of a coordinating agency, asking people, putting them all together, and then, technically together, and then building a system or a hydrogen valley technically. And it'll take time. It'll take a lot of, it took us 10 years to reach this stage. Thank you very much.